right, are we live? Hello, hello, hello. So, welcome. Another question here to look at. So, give me just one moment. Okay. Combination sum 4. See how that goes. Given an array of distinct integers nums and a target integer target, to return the number of possible combinations that add up to target. The answer is guaranteed to fit a 32-bit integer. Okay. It's a pretty interesting question. Let me see. A couple things. So, this looks like a backtracking question. numbers between 1 and 1,000. All unique targets between 1 and 1,000. Okay, yeah, backtracking should be fine. Should be fine. Negative numbers are allowed in the given array. How does it change the problem limitation to add to the question about negative numbers? Yeah, negative numbers makes it complicated, huh? Either backtracking or dynamic programming or some variation of these things. Yeah. I think actually dynamic programming works okay, but it does make it more challenging if you add negative numbers. Gets a little complicated. So what I want to do? I want to check something. Yeah. Okay. And I also. All right. Let's try to code up a solution, because I think I already have a solution. Basically, you could do this recursively and say whatever the target is for each number in the array, you select that number and subtract it from the target, and then recurse on the set of all of the other numbers, right? The set that's missing that number. And it's going to be that's more of a backtracking thing, though. It's not really a dynamic programming thing, is it? I've solved questions like this before. Oh, excuse me. These are actually, you can copy these a few times. Oh, that's interesting. So it's not, they're reusable. They're not, the way this is being described, these values aren't, they're distinct, but they're not, they can be reused, right? So actually then you can, by the way, this is equivalent to the number of ways that you can make change, or this is a similar kind of a problem to the number of ways that you can make change. So like if you had $1, how many ways, if you have quarters, nickels, and pennies and dimes, how many ways can you make up $1? Or this is sort of an equivalent question, similar question. Actually, I think it's almost exactly the same. But yeah, actually in that case, you can do it recursively then, dynamically. It's actually, I think, more efficient if you do it, if that restrictions are not there, because you can reuse, like the state stays the same, well, the possible options you have are all the same. So really it's the sum of all of the previous, yeah, so okay, we'll go like this. This should give you the right answer. Just to call it recurse. I think this is like a really simple question then, if that restriction's not there. So I think it's a little more complicated, a little more challenging, and computationally more difficult if you can't reuse these values. But if you can reuse them, I don't think it's a problem. So, okay, so the way you do it is int x, let's say, and we're just going to use nums directly, right, or use it through here. And we're going to say int ret equals 0 for int I equals, so for auto x and nums, or not x, yeah, we'll go target, or t, call it t. Nums, you take ret plus equals f of t minus x, and return ret. I think it's that simple. I want to memoize this too. I don't think we need this vector, or, well, yeah, okay. And unordered map to memoize. Base case, if t is less than or equal to 0, return 0. Now, actually, that's a good question. What are the constraints? It's going to be at least 1, right? Okay. Yeah, I don't know. Actually, that's a good question. I wonder if this should be, the base case should be a 1 or a 0 if you're less than 0. I think it's a 1 if it's a 0. And then I think this is 0. Yeah, I'm going to say something like that. I think that's correct. I think doing it a different way is not right. So yeah, and then we say if memo.count of t, return memo of t, otherwise. Now, your memoize, so here, this is a quadratic time solution, and the reason it's quadratic is because you're iterating over this variable, right, through the recursion, and you have an inner loop that calls the function recursively. So even though this function would be basically constant time once it's memoized, because you're calling it, you have a linear term inside, and you have one term that you're looping over, you're going to end up with a quadratic time solution. Excuse me, after memoizing. And this should be target curse. Something like this would solve this problem. Yeah. What are some? Now, do we handle the edge cases properly? I think we do. And we said pennies, nickels, dimes, quarters, and $1, right? Oh. 1 to 1,000, no, okay, all right, sure. Fit in a 32-bit integer, oh, nice, really? No kidding. You're kidding. Oh, this supposed to be under 1,000, right? Which one is that? It's causing me so much trouble. Is it the? It's this one? Oh wow! Whoops. Okay. No kidding. Wow. Whoa. Whoa. These are large numbers. I was wondering, I was like, this computationally this shouldn't be too bad, but actually the issue is the reason these bounds are there is not because the it's too hard of a question. It's because of the size of the possibilities. What you can do is, if you wanted to sort of make these bounds larger, is you could. Oh no, actually, never mind. No, that's about right. If it's quadratic time, then 1,000 is about right. Yeah. What about these two? No kidding, really. Let me make this like 100 then. 10 or 50. Is this the one that's causing issues? Or they both have issues. Wow. Apparently there are a lot of ways to... Oh yeah, because you could do... These aren't the unique combinations. These are... Oh, that's interesting. I didn't really think about that. Oh, there's a lot of those. There are a lot of those. Oh, we gotta get rid of the one then. Yeah, the one is gonna be too much. The one's gonna be too much. I didn't think about that. Wow. Okay. I think we're okay. You know, I don't know. I don't know if we're correct or not. I couldn't tell you. Okay, let's go for it. Hey, you got there. Sweet. Let's see if we can get 0% or 0 milliseconds. A couple more times. Yeah, there we go, 100%. All right, not bad. Yeah, that's not too bad. So there's probably more to talk about here. So a couple things would be like, if they couldn't be unique, right? That would make the problem more interesting. In other words, like if 112 is equivalent to 121, which is equivalent to 211. These are in some sense equivalent. If you had coins, right, it would be 2 pennies and a 2-cent penny or a 2-cent coin, and that would sort of be one combination. These are actually permutations. These aren't combinations. So that's interesting. I didn't really think about that, but yeah. And the fact that you only have 1,000 to worry about makes it not too bad as well. I could be wrong also when I say that this is a... No, it is... Oh, well, okay. It is quadratic, however, target... So it's not quite quadratic. There's like... Depends on the target, and it also depends on the number of numbers here. But basically, this is like a constant, I guess. This loop, you could basically consider this to be a constant, and in that case, this is actually linear time, not quadratic, which is why it was actually pretty fast. Yeah. Anyway, okay, pretty interesting. Yeah, one constraint that would make things more interesting would be if you couldn't repeat the values, and then another constraint would be if you couldn't repeat the values, and also if you could not have what do you call that? If permutations were considered to be the same. So that would add some more extra, would be more interesting. I think if this set is relatively small, this nums set, especially if the target is relatively small, if these values are relatively small, then it's not too bad to do kind of a brute force solution over the, like a backtracking solution over the, yeah, I get a depth first search solution over the numbers, you know, like sort of which combinations of the numbers would give you, of the distinct numbers, of the unique numbers, will give you that particular target. Pretty interesting question though. Yeah, not too bad. I think we did okay. Alrighty. Yeah. So how was that? 15 minutes? That's not too bad. So let's let's go full screen for a moment, and let me end it here and say thank you for watching. I'm going to go ahead and thanks for watching. I'm going to go ahead and go to the next question and take a small moment. Probably listen to some music briefly. So yeah, thanks.